Hello, everyone. Welcome. I think we still have people streaming in, maybe. We'll start in about a minute. Hopefully you can hear me and you can see the screen. Is that right, Zoom?
Yeah.
Sweet. Awesome. Stable number on Zoom, I think. So I might just get going. It is being recorded, so if you do miss anything, you can check it out once I put up the recording. Okay. Maybe we should enable closed captioning, because then I can talk about it. Maybe it is working. It is. Excellent. We'll actually discuss how that uses AI as well. All right. I'm going to get started. Okay. Welcome to the Summer of AI. Thank you for joining me and everybody else who's on board. We'll have volunteers and other staff and academics around UQ talking on various topics. I'm Shekhar, and I'm going to lead you in this opening seminar to explain a few things. Firstly, some of you may already know the impact that AI is having. Why bother with AI? So I'm just going to briefly go over the huge amount of impact it's having, and in such a short period of time I have never experienced, and many academics who have been in research for a few decades, if not more, have never experienced such a short turnaround. See that the turnaround in new developments that are groundbreaking, changes to society that happen in the span of weeks now. We'll talk about ChatGPT very soon. But so that's the first objective. Second objective is to show you that it's not a fluke, all right? And in fact, hopefully by the end of this, you'll be like, why didn't it happen sooner? You'll see that everything does happen, may appear to be a black box. And in some ways, when you build your models, there will be elements of black boxness. But you'll see that for the large part, you can believe it. It can do it because of the mathematical framework that's behind all of this development. It's a culmination of wonderful factors that we're where we are in AI right now. And thirdly, I'm going to go through all of the different events that are happening, what it means for you, how you can interact, and hopefully the advantages you gain from attending it. So we can keep the attendance numbers high, and so we can keep interactions high. Okay, it's cool. So at the moment, we've got around 20 people. We've got a couple of people here in person, 20 people on Zoom, and I'm sure there'll be many who are watching this recording. Hi to you. Thanks for joining us. All right, so firstly, impact of AI. Now, this slide is interesting because it's evolved over a few years, and the beginning of which started something like this. Wow, AI can do live transcribing, which is currently being shown in Zoom right now as I'm speaking, which is awesome. It's sometimes a bit off, but for the most part, it works. I just want to say that this stuff that you're seeing right now is old news, all right? This stuff is old news, in fact, all right? This was only 3 to 4 years ago, but this is very much old news. And of course, these guys are doing it. You know, they're all adopting it. 2 years ago, I would have shown you this picture and asked you, isn't it amazing that that person doesn't actually exist? It's fully computer generated, all right? That actual person does not actually exist. As of now, though, this is pretty old tech. And I'll talk about the new tech note now, but most of this, sorry, this is blocking the view. Oops. I'm just going to pin my video for those in person so it's easier. There we go. Most of this is basically due to deep learning. There's other aspects, but we'll get to that soon. But most of it is deep learning. And essentially, before I go on to the rest of the content, a quick overview of why we're calling this AI. Some of the academics in the field will be cringing at the term AI because it's a very generic term, doesn't really mean anything. I'll tell you why I use the term AI. AI is a multidisciplinary field. It's got lots of subgenres and academic areas and research areas. And it's much easier to say AI than to say, what we're trying to cover in this summer is machine learning, deep learning, reinforcement learning, optimization, physics learning, and all these sorts of things. It gets very cluttered very quickly. So AI is a nice term that brings all of this together. So machine learning is something that started all of this a while ago. And that's sort of, I know some of my colleagues won't be that impressed if I call it more of the past. Deep learning is something that we're currently using right now. So that's the in thing right now. And I suspect in the future, it's going to be more reinforcement learning as we begin to discover new things and ideas. All right. 2 years ago, you could do these wonderful things and they look pretty impressive. So you type something in. This is GPT-3. And you could generate images from text. This looked impressive, but this is so outdated now, as you'll see. You could also do things like do design things by just typing stuff in, and you would generate things. And that was great too. And so that's also a couple of years ago. Last year, you would have seen something called DALL-E. And suddenly we could do a little bit more than what we could do with GPT-3. AI generated faces. And so you type something in. Quite interestingly, a manga, which is like a comic, Japanese version of a comic. You have Elon Musk, obviously, and then you have Tesla, and it could put all of those together. That was pretty good. This was last year, okay? This is obsolete now. Here's what we got 2 weeks ago. OpenAI released, you can call it a chatbot, but it's really GPT 3.5. And here you can write a text prompt and it will write up to an essay for you. In fact, it can write grants. Many academics will be happy to know. And this has obviously profound implications, especially if you are trying to write assessments. Essays may not be what you want to give as assessments these days. But here is a tweet. So I'm going to actually switch over now to, I'll release these slides, and there's links on these slides, and they go straight to the Twitter pages. So I'm just going to switch over to my browser. And then switch over to this. Maybe you can't see make it bigger, maybe. So this has got a lot of likes. And it's quite an interesting text prompt. So you write a text prompt into this chat thing, and GPT 3.5 will respond. It also keeps a history of your chat and uses that to put things into context. So it's a bit more advanced than anything we've seen before. And for those of you who don't know what a VCR is, it's sort of a tape-based playing device. Anyway, and I don't know about you, but that's scarily quite good. That, you know, in biblical verse, like the Bible, how can you remove a peanut butter sandwich from a VCR? It's completely absurd, but yet, let's scroll down. You can read it for yourself once you get the slide. It's pretty good. There are other examples where you can get an explained version with code of the bubble sort algorithm in a very obscure programming language. I can't say the name because it has a swear word in it. But you can find lots of examples and even explanations for Git. I was hoping to have some, maybe I'll post some of these interesting tweets into the Slack page. You can see them for yourself. But this is actually pretty amazing. It was released 2 weeks ago by OpenAI. We will be talking about something called stable diffusion. And here's a video. And the video is edited near real time, where you write a text prompt and each of the slides is put together. Well, I can't say that that was actually a video edited in real time, but certainly the images were, and then they were put together into a video. So and this is just an example of one of the few things that some of these models can now do. And, you know, an enchanted forest, sure. It looks pretty much like what I would think of as enchanted forest, an alien civilization is in the background. Sorry, that thing's getting in the way. What else do I want to show? All right, some of these images here, high quality images generated by these models. And they can do a lot of things. This is a nice actual explanation of how it works. I won't go into how it works. We have an entire day on Friday for that, okay? If you're interested, we'll go right into the technical nitty-gritty details of it. But suffice to say, it's damn good in what it can do, considering what we've seen in the past as well. Any other images? There's some technical explanations. Here's a nice one. You can interpolate what the person looks like under the face. I don't know. There's various examples of in-painting. So you remove stuff, the model puts it back in for you. That's what in-painting is. You draw something and it'll basically interpret it, and put a scene in for you. So it's a bit of a game changer. The paper for this, for those who are in research, the paper for this is not even published yet. It was submitted, well, I guess it was, sorry, let me backtrack. So it is this conference, which was done probably 6 months ago. And the paper itself was released a few months before that. So it was released in a conference, which is one of the most highly cited publications in the world, right behind Nature and Science, which is Computer Vision and Pattern Recognition, CVPR. And so this was a publication in CVPR 2022. Since then, in that less than 12 months, a company has been formed called Stability AI. They've released Stable Diffusion, and they've got $100 million of investment, and they are releasing everything open source. So one of the things you'll see is that these things, which are making huge impact, is because they're all freely available to use, and the entire code base. You can download them, run them on your own machine at any time. Just few more examples if student gets out of the way. So here's an example of a realistic generated images. Here's another one. I don't know what the text prompts were for these, unfortunately, but this is the latest version, released a few weeks ago. It's pretty good. So that was the old one. Now it's high resolution. You can give it a text prompt and an image prompt, and it will make stuff up for you. You can interpret depth to image data as well. In painting, so you can in-paint, right? So you have a fixed mouth, it will draw around it. Yeah, other details. Look, some of these links I'll share. And this paper isn't even, or will be presented in Neuronips, which was literally 2 weeks ago. It's already doing development now. It's 20 times faster. And instead of taking 1,000 steps, it now takes 4. And you get the same realistic images. So you can get text-guided image generation. You can get conditional. So if you want a dog, it'll generate dogs. In Paint, image-to-image translation. So, you give that the input, and you can get all sorts of outputs based on the style you want. All right, so there's heaps of examples out there. I've only shown you a few, but that's what it's all about at the moment. So let me go back to my slides. So, and you can click on those are the links. And this work itself is going to change anything related to text or imaging, which is quite a large field. And of course, that model itself doesn't necessarily have to be image or text. Right now, it is image and text, but basically the whole idea of this diffusion, and you'll see on Friday, it's got nothing to do with images or text. It's just to do with data and neural networks, okay? So whatever data you have, you should be able to apply this technique. It's a form of generative modeling. So you take your data, you find out what the data distribution is. And if you understand the data distribution, you don't need the data anymore. You've got the distribution. If you have the distribution, you can do anything you like with it. Okay, that means you can just sample points on it. And that's what this stuff is doing. So when you write a text prompt, it basically puts you somewhere on it's called a manifold. It's a curved surface or a distribution. You write some text. The text points you, the model, to the right point on the manifold. So if this is a tennis court next to a volcano, and there's someone's playing, and you can actually give this as the context as well. You can give images or text. It can pull out all of this information that you see there about the volcano and things on that data distribution and actually sample and then generate an image out of it. And that's what this thing can do. It just so turns out that you need a lot of data and power for this. So the next question you're asking is probably how much hardware and data did they use? Apparently, the amount of hardware that they used was 1,000 GPUs trained over 1 month, nonstop. Give you in context of how many GPUs UQ has in total, it'll probably be under 100. And that's of different scales. So you're talking about some older ones, some newer ones. They had 1,000 new ones. So it does take a bit of training. But the interesting thing is there are other techniques called transfer learning where you take a model which is already trained and then apply it to your own data. And if you're in imaging or in text, you can certainly do this. All right, anyway. Convinced you so far, let's get down to the science of why you should still bother. Why would you bother with AI still? In the 70s, it was said that computer vision would be one of the most important problems. And if we could solve that, it's the relatively simple problem. It's the first step to AI, proper AI. And we should be able to solve it because it's fairly simple. You just look at something, you know what it is. I mean, what could be more simpler? Yeah, 50 years later, we are now finally close to a solution. And there's a Nature paper there about it. And here's an example of the type of timescales we're talking about. So 2012 is where all of this stuff started, and now we're beyond human level performance at the moment. And you just saw Stable diffusion occurred roughly 12 months ago. It's already extended 6 months ago. Chat GPT 2 weeks ago. Yeah, it took about 30 years to get to that point. Okay, so that's computer vision. Protein folding using graph neural networks. Again, in Nature, DeepMind, sorry. They found a way to fold proteins and study the way they're folded and to discover new ones. So in 2016, it was not that bad. And now, they've basically solved the problem into the plus 80% of trying to model these things. It took 50 years to get there. And it took 4 years to get to this point. So another Nature paper, we can use AI to help humans discover new mathematical theorems. Looking forward to those types of tools to become more mainstream. Stuff that I'm interested in, another Nature paper, we can replace entire transformed domains. And we'll see why. So that's fair evidence. But what I want to show you next is the mathematics behind why this can happen. Is it a fluke? And what I'll show you, it isn't. Actually, before I do that, this is actually not the first time this sort of thing has happened. You'd be surprised, although maybe not at the scale that we're seeing today. We have actually had these sorts of bursts, and then we've had the bubble burst. And each time it's been because of a theoretical problem that has come in the way. And you'd be surprised, or maybe not surprised to know, that most of them are related to artificial neural networks. So what is an artificial neuron? Now, I guess one way you could justify why we're seeing such important advancements in AI is obviously we are using artificial neural networks, very simple models that you'll soon see, but it shouldn't come as a surprise, because the neurons in our brain are quite, well, when you put them together and create a brain like ours, we've been capable, and you can see the evidence that what we're capable of. So even with a simplified model, surely we can do amazing things, and that's what we're beginning to do. And our model is naively simple. It could not be more simple. You basically have some inputs. They could be from anywhere. Usually either they come from an input itself or from other neurons, outputs of other neurons. And you do a weighted sum of those inputs. So W subscript 0, subscript 1, subscript 2, etc. You are doing a weighted sum. You have some bias, which is just an offset. And I guess the key thing here is this activation function. In our very simplified version, all we're doing is creating a nonlinear switch of a weighted input. So you take a weighted input and then you decide, am I actually going to send an output? Do I weight it somehow? Or do I just switch off? And this is the output. So it's the weighted sum of plus some offset going through some activation function. Put them together in a hierarchical fashion, and that's all what deep learning is. Okay? Because we're so early stages in our AI development, we think of them, currently we think of them as layers. We put these neurons together in layers just because it's more structured. And in fact, this thing was created in the 1950s. It's called a perceptron. And here you have neurons, and these neurons are just inputs. And you have a hidden layer, so you have hidden layer or hidden layers. And they're just neurons that are, in the beginning, they have no information in them. You don't know what they should be. But you do know that you expect some sort of outcome. So given an input, you're supposed to get some sort of outcome or output. And all we do is we have a training procedure where we learn the weights between all the neurons for a given output. Obviously, if you have only one pair of input and output, you could have many solutions for the hidden layer. Which is the optimal solution? You don't know. So what you do need is lots of input and output pairs, and in fact, quite a large number. Okay, the result comes out, and we usually call the output layer the label. It's a very simplified version. There's the original paper. And the idea that it was called the perceptron. And it's basically, you're going from an input and you're trying to make a prediction at the end of some sort of class or regression. As a link to a nice video where you can see it all visualized and how it works. I don't have the time to go through that, but I'll be sharing the slides, and so you can have a look through if you still like more details. And of course, we'll go through some of these details during our deep learning crash course tomorrow. You can pair these things, or you can make hierarchical representations of these things in something called a convolutional neural network, which is designed for computer vision. Now, in a previous slide here, each neuron in this layer is actually connected to every other neuron in the previous layer, sometimes referred to as dense connections. Now, if you have many neurons and many inputs and many hidden layers and many neurons in a hidden layer, that's a lot of weights to learn. In an image, actually the neighborhoods are what's important. So what makes an eye is really the pupil and the eyelashes and the eyeball. That isn't really related to the mouth or the nose that much in the immediate fashion. But later on it is, because you need two eyeballs and a nose and a mouth to make a face. So a convolutional neural network is easily thought of as something that learns neighborhoods and then proceeds to learn the neighborhoods of the neighborhoods. Hierarchical fashion. So in the beginning, when you're just looking at the eye or the pixels, say, around the eye, around a pixel in an eye, you want to learn the distribution of pixels around the eye. But later on, as you do look at the neighborhoods of the neighborhoods of the neighborhoods, you will begin to see the whole eye and all the different representations of eyes and noses and mouths. And even later on, you finally put all those neighborhoods together to form a representation of faces. And at some point, you then put all of those features together, aggregate them to make a decision. And that's basically how a neural network will work. And we'll cover those in details in later lectures. But why is the surge in AI now? Neural networks has been around for a while. So in the 50s, we've had different winters. And the problem is you have many weights. As you saw, for every neuron, you're going to be connected to every other neuron, and it's done in hierarchical layers. So you have many, many weights. How do you learn all of those weights? And the answer is through parallel processing. So we have these things called graphical processing units. We're going to have an introduction to them tomorrow during the training or during the AI support lecture at 10 a.m., I think. We'll describe them in more detail then. But basically, do a quick description here as well. But basically, these are processing units which are heavily multi-threaded, and they do matrix multiplication really, really fast. That's basically all they do. Matrix multiplication really, really fast. There are some other reasons we now have that hardware. We also have the data, and we have the high-speed internet to make it the data available, and the code and the models freely available. We have had some recent developments that are roadblocks of neural networks also solved, backpropagation being one of them. Again, some technical details that you don't need to understand right now. But all of those things, everything is open source. We've got heaps of data, and we've got the hardware now to crunch it. So now we can build these models. The key question is, even if we have all of those, why are neural networks able to achieve these things? And you'd be, one of the most wonderful things that I learned about when I was looking into these things is that there is a mathematical theorem called the universal approximation theorem that is basically the heart and soul of this result. So you can be rest assured that all the deep learning that you're doing does have some mathematical background, even though we don't have specifics, and we'll probably will in the future. But it comes down to the fact that any neural network, or a neural network, can approximate any continuous function with arbitrary precision with just a single hidden layer. That means, there's an example there, take any continuous, whether linear or non-linear function, can be approximated with just a single hidden layer. So that means you can learn, without having to understand the mapping, one set of values to another set of values. It may be a measurement of human motion to an animation or some sort of pathology or some sort of other human motion. It can be anything. So as long as there's a mapping involved, a neural network can learn it. So you've seen the examples I've shown that you can take a text representation and you can map it to an image, okay? And that's what the stable diffusion stuff kind of does, okay? Now, it says a single hidden layer. Turns out, as you add, so for example, if you wanted infinite precision, so this is arbitrary precision, but if you want infinite precision, you need an infinite number of neurons in the hidden layer. So it has to be wide. So we call it, if you're looking at it from sort of left to right, going from green to blue, and you're trying to traverse these arrows, it looks like it would be infinitely wide. So an infinitely wide network, which we call the connections between neurons, would be able to be exact representation of a continuous function. What people have found, there's another theorem, I haven't got it here, but there's another theorem that shows as you add layers, you don't need the network to be that wide. So if I add another layer, those two layers no longer need to be infinite. In fact, they become bounded. And as you add layers, so you add more and more layers, your network retains the power of this approximation theorem, but needing less and less neurons, okay? Maybe not less connections, but less neurons. And that is why it's called deep learning, okay? It's deep, so not wide, but it's deep because it has many layers. In fact, the more layers it has, the more powerful it becomes. There are other machine learning considerations that come into play if you have too many layers, overfitting and whatnot, but we'll get to that later. Yeah, I'll find that out for you. Yep. Surprisingly, that proof was around 2006. So not that long ago. And that's actually an active area still, okay? We can, okay. Oops. So what's the intuition behind this universal approximation theorem? It's actually not too bad. Every neuron basically contributes a little bit. It's a very simple linear manipulation. Each neuron has a small linear manipulation, and they're all divvy up, but they're all sort of weightedly summed to make a complicated function. So you have all of these neurons, but all of these neurons sort of make a small contribution to approximate the function. Now, this result is really good. As I said, we can do things like I may take an image of something, but then I may take, for example, an image of a human body or part of a human body, and then completely unrelated, I know that part of that human body changes in such a way that you end up with a disease. I don't need to understand all of the complex interactions that have occurred. All I know is that this image turns into a diseased one. Can I learn that mapping? Yes. Actually, there's heaps of work. That's what we try to do here at UQ in biomedical imaging. We have networks that do precisely this. We learn these nonlinear maps. We don't need to understand all of it. Later on, we might begin to look into it. But what we want to do is have these neurons on neural networks learn for us. Okay, moving on. As I said, they can approximate any nonlinear function. And here's kind of the intuition of how they work. What it does, the neural network does, is it builds a curved, so it looks at the data as a curved surface. So on the left, you have one where data is on a one-dimensional surface. And all a neural network does is it deforms that data distribution surface while maintaining it as a manifold. And a manifold means that the surface remains differentiable and locally linear, flat, locally flat. It still can be curved globally. And it deforms that manifold to suit the task. So in this case, we want to separate the red from the blue. Okay, let's deform the manifold so that it's easy to separate the red from the blue. On the right, you see the example where the image is two-dimensional, or the data distribution is two-dimensional, and your data is actually a spiral. And you're probably like, whoa, how do I separate those two? In a way, we can, because we can see two separate spirals. But how do you do that in terms of actual mathematical values? Oh, easy. I'll just create a manifold. The neural network says, I'll just create a manifold where you can basically separate the two data sets completely independently, to be independent in that way, okay? And this is the, I guess, the crux of what neural networks do. They learn manifolds, all right? Which brings you to interesting point. Just a comment from me. All the models you've seen with diffusion and GPT-3, chat GPT 3.5, whatever, they all learn manifolds. They don't create new data though, okay? So that's an interesting question. Even if these models are so complex and interesting, do they actually learn anything new? And the answer is probably not. Okay. Some other advantages. You have a neural network, it looks like this, and you've learned all the weights. The great thing is these weights are just basically matrices, as I said before. And to actually run data through your network, you may not know what I is, or I may change based on, you might have different images and you want to see what happens and what outputs you get. So I might be different, but all of these you've learned it, you've trained it. And so to run data through a network is incredibly fast because all you've got to do is do these matrix multiplications. And again, this is outdated hardware, 3 years old. It has 10 teraflops. A flop is a floating point operation. So these things can run inferences in less than a second in large networks. As I said, they're highly parallelizable, and see some examples of how much progress we've made in 10 years. But you'll be familiar with a CPU, and we'll go in this detail tomorrow. A CPU probably you might have seen that it has like 4, 8, 12 cores, and then you have main memory. And a GPU, you have nowadays 10,000 cores, okay? 10,000 of these, and the memory bandwidth here is much better, and this is faster memory. So each one of these little cells can handle a little bit of the matrix multiplication, and so you can do all of this, several thousand times faster. Here's again, it's a video, you can have a look at yourself, but back in 2000s, this is what there's a mesh representation here, an animation. This is what it looked like. And here, this is all done in real time with ray tracing. So you trace every element of light, bounce off to display all of the realistic graphics. And this is, again, a bit outdated. It's a couple of years old. And I said our model of the neural network is quite simple. And the main reason why these things are so good is because of this nonlinear activation. And here's an example of which. And this basically acts as the switch. It kind of instructs the neural network when to fire. And this is what gives it the nonlinear properties. So sometimes the choices that we make here for this function actually do make a big difference in the type of task that we take or do and the performance that we get. And so basically, the ones that you're probably most likely to use are this ReLU. So it's a switch. So, if there's not enough activation, it doesn't do anything. And then if there's enough of a weighted sum, then it actually passes on the signal. There's some other ones here where this is the most traditional one, where if you want a probabilistic output between 0 and 1, that's what it will look like. This is normalized between 0 and 1. And sometimes for practical reasons, you don't want to kill the signal. You just want to really make it negative so it doesn't have a positive effect on your output. And all of this would not be possible without stochastic gradient descent. And this is where machine learning and optimization theory is absolutely critical, because in the end, you need to find the set of weights that gives you the optimal performance output. And again, there's a link here if you'd like to see. It's a great video. But basically, this is what we're doing. If we have a parameter space, and maybe one of those balls represents the state of the entire neural network, we want to adjust the parameters, in this case, the weights of the neural network, ever so slightly, so that it descends this cost function or this space. And it's a cost function, so you want the minimal cost, which is the global. Well, here you have a local minima and a global minima. Ideally, you wanted the global minima, but the best we have theorems for are guaranteed minima. It could be either. Optimization theorists in the chat or audience might correct me, but most stochastic gradient, or most gradient descent algorithms guarantee finding the minima. They can't guarantee whether it's going to be global or not. But anyway, so what optimization does is it basically finds a set of parameters that gives you the lowest cost. And the choice of the cost function is going to be important. We'll see when we do the course or crash course tomorrow. Your choice of cost function will define the way your network is going to converge and the performance that you're going to get. Now, the other thing that's really good is that when you're learning these weights, so in the CNN, for example, when you learn the weights, you end up learning these features in your data set. For example, in the CNN, we learned the neighborhoods of the neighborhoods of the neighborhoods. Now, it turns out if you look at the neighborhoods of the neighborhoods, you're kind of looking at edges. And that sort of feature extraction is actually becoming data-driven because it is driven by the optimization process and the cost function you've chosen. So what happens is, and this is my favorite part of deep learning, is being able to have a data-driven approach to your data. So here's an example where you try to build a network that classifies the types of dogs or breeds of dogs. And then you have a look at, all right, you've got so-and-so accuracy. What are you actually looking at? What features, parts of the dog are you actually looking at to make these decisions? Lo and behold, it's the snout and the ears and maybe the eyes, right? Which makes sense, okay? There's a nice video here that shows a very simple neural network called the VGG network and how it classifies fruit and where it's looking to do it. You're welcome to have a look. And here's a real-time example. As I said, you have fast inference, so you run these things in real time. You can have a look at where it's looking as someone's walking around in a European city, where the neural network is looking at and what its classification is. So here it ends up showing that it's a bicycle, and it's looking at all the bicycles to decide. Again, a video. And this is why I also like it where deep learning sort of outperforms machine learning, traditional machine learning anyway, and statistical methods. So there's a sort of misconception that deep learning is statistics, or it's just finding principal components, or it's linear classification or decision boundaries. Deep learning doesn't suffer with issues such as other algorithms where you have the curse of dimensionality and you the more data that you add, the performance plateaus. In fact, deep learning, this curve is now found to be exponential, where it actually gets even better as you add more data. And ChatGPT and Stable Diffusion are some examples of how that's been happening. Okay, so they have millions of parameters, and you would think they require millions of samples. Somehow these networks still learn down here, even though we don't have enough samples as well. So that's the area of research. But as a rule of thumb, if you have very little data, you could probably still use machine learning and other algorithms down here. But as you get up around the thousands, you probably will gain by looking at deep learning. Lastly, some comments of what has been found is that if you do use deep learning, because it's data-driven, because it does all the things I've mentioned already, it turns out these things, because they use GPUs, if you get the same algorithm that accomplishes the same task using deep learning rather than other methods, it can be up to 1,000 times faster while being 20% more accurate. That's my experience. And that's the kind of impact that these types of techniques are having on science, right? And it's completely data-driven. So it does not have biases unless you want it to, or you are not careful enough with your training data. Now, usually I talk about an example in imaging, but I'm going to skip over it. The slides will be available, but you can sort of go through it. But basically, the gist is, if I got an expert to look at a set of MRI data for 1,000 patients, it could take 7 years for them to process it. And roughly that corresponds to a very experienced radiologist, right? He would probably take around 7 to 10 years to become a senior person in that role and highly trained. A deep learning model can process all of that data in less than a day. So we can now look at entire data sets in meaningful time where we couldn't before. And this is the problem now. And we can solve it with automation. So quick summary, best performance, data-driven, milliseconds in processing, lots of data, nonlinear mappings. Problems? Lots of parameters, not suited for small problems, okay? Training can take hours. As I said, for Stable Diffusion, it took 1,000 GPUs and 1 month to train. That's a lot of power as well, electricity. So if you have 150 samples, you're probably not going to get a good extra performance. But if you're in the tens of thousands, you're definitely going to see performance increases. If you have 150 samples, you might just look at random forests, which is still pretty good. They can do linear regression, but then just use normal models to do that. Some misconceptions: is it just a tool? In my opinion, it is not. Reason? Because AI requires your specific data. And it requires optimization of your problem, which means your data and your optimization need to be embedded within your data or research area or domain-specific area, which means you need to consider AI as part of the system. Isn't AI just statistics? Well, even with Stable Diffusion, you'll see that when we go through it on Friday, the first theory built around it was using statistical and probability models. But because the statistical model works, doesn't mean that neural networks run on statistics. It's like the theory of statistical mechanics. You can do quite a lot with statistical mechanics. I would argue that you can't do all of it, though. I think we need an entirely new theory for neural networks, but that's just me. All right. So hopefully at this point, I have convinced you that AI is of impact and that it's not a fluke and something that has good grounding and good reasons for why it is. Now, lastly, why the Summer of AI and why you should take part in these events. It's going to be cool. So start off with what are the good things you're going to get? You'll get opportunities. So you'll get to see where AI is making the impacts, where the opportunities lie. Obviously, it's professional development, even if you're a staff or a student. You will be able to do all of this. It's all open source, right? You can run it on your desktop. With the Summer of AI, it's moving really rapidly. In fact, one would have thought, yeah, maybe 2018 was probably the peak. It would probably start to taper down. It's actually accelerating. So the way we're going to have to keep up is through. No one person is going to be able to read the papers. I think there's something like 1,000 papers a month at the moment being put up on archive.org. There might be employment opportunities to connect. Researchers are looking for those. For us, it's an opportunity to help researchers, especially to make sure that UQ researchers get an advantage when using AI. For us AI researchers, maybe we'll get some new connections and some PhD students out of it. What are the events that are happening? So I know we want to cater for those who are new to AI, as well as those that are using deep learning a lot, but even for those who know deep learning a lot, for example, for myself, I haven't actually gotten that much information on diffusion. I want to know how it works. So I'm going to be really, really keen on Friday when the experts are going to be talking on Friday. Tomorrow, but every week, we will be covering how to get started. And this week, we're going to do a crash course in deep learning. So hopefully you can get some way to start your AI journey. Day of AI, Friday, every Friday for the next 3 weeks, we're going to be covering an incredibly important model. So this week we're doing diffusion, stable diffusion on Friday. Next week, we're going to be doing transformers, which is the basis of GPT, okay? So you'll get to see and play around with the best models in AI. Some of you have already started using AI. So we're developing materials, training materials for you to learn how to train, use, optimize, and even deploy models. So we'll be having talks tomorrow about where to find GPUs, how to train them, how to use the compute resources here at UQ. Next week, we're going to have someone talk about how to optimize your models and GPU profile your models so you get the best out of it. And the week after that, I'm hoping we can talk about how to deploy these models. Maybe you want to deploy them in a commercial setting, in a medical setting. How you're going to do that, we'll cover that as well. I know a lot of you are not sure which model to use, or have tried a model, it doesn't work, and you want advice. And so I'll be around, other experts will be around to help staff and students in their problems or their projects. We have a lot of summer scholars and II interns, so they will also get some help. And a hacky hour, which is sort of like you come down and you have a tech problem with one of your AI stuff, especially for summer scholars and interns, will be around to help as well. And we want to disseminate the knowledge. So what's happening? What are some works that have recently been published in UQ by UQ researchers, but also in general, of general interest for the AI community? What is the last one? So the last one is this slot next week and the week after at this venue. So we'll have some state-of-the-art ideas, and then we'll have like researchers who have either published that work or published in that space, but there's another high-quality publication, like a CVPR publication, and that they will do a journal club. And the idea there is good for me, especially because then I don't have to read the paper that much. I can just come to those sessions and then digest everything in 10-minute blocks. And we'll try to do multiple of those together with us so I think next week we'll concentrate on transformers. So we'll have transformer talks. And I'm still organizing the individual talks, so I'll let you know which talks are when. And so that's probably good for all the AI researchers, but also good for the general to see the types of works and where they're going. Just a quick summary of, what's in it for all of you. So, you get to master deep learning. Even we're going to get to experts and deep learning people as well. Hopefully, some of you researchers will find new energetic students and volunteers. Previous years, last year, I know a few students have found researchers and projects that they want to work on. So something I didn't mention in the previous slide, we're going to have a projects showcase of prominent researchers who have projects but don't have people to fill those projects. So all of you students out there or developers out there looking for opportunities, I'll let you know about that session where you will see lots of a showcase of all the projects that are happening and what these projects actually need. So you'll get an opportunity to see that. And hopefully we can also share our software. All right. The other thing I want to reach out to is also the AI researchers like myself and others, we all have developed code already. And you'll see as part of the AI showcase, the code for all those things are available. Some of them are open source, some of them are yet to come out. And so we want to see it as an opportunity to collaborate with you as a UQ researcher as well. So we'll be able to, depending on the model that you choose and what you're trying to run, maybe we'll have code already for you to go, for you to use. So in conclusion, I'm going a few minutes over. Neural networks are what's that's responsible for this evolution. The benefits include being more accurate, faster, and handle nonlinear data. And most data in the real world is nonlinear. So these opportunities for the AI exist in every research area, okay? And so AI skills are in high demand. So all of you who are new to the research space, PhD students especially, or summer scholars, your skills that you develop probably during the summer will be in very high demand. And hopefully summer of AI will get you where you need. All right, I think that's it. A couple of questions. So is it similar to manifold learning? Yes, yes it is. It is manifold learning. It is indeed manifold learning. Could you suggest just a software stack to get started? By software stack, you mean a framework? So you could use PyTorch or TensorFlow or JAX. And if you just want machine learning, scikit-learn. We got TensorFlow, PyTorch, JAX, or scikit-learn. The two big ones are TensorFlow and PyTorch. If you're really, really keen on NumPy and you're a big NumPy person, then I would have a look at JAX first, okay? Because JAX is just NumPy for deep learning. PyTorch and TensorFlow sort of re-implement NumPy for, it's a bit complicated, we'll explain it tomorrow, but they use a computational graph. JAX is just NumPy. Scikit-learn has neural networks in it. It's not really for deep learning though, but if you're doing machine learning, then that's pretty good. So random forests, we're using PyTorch, a good question. We're going to use both. I'll probably show you both at the same time when I teach. That way you see the differences are not that different. And it's easy to adapt actually between the, I might show JAX as well. You just choose one. It doesn't really matter at this stage. When you get down to maybe if you're trying to create new models, like new actual deep learning methods, then it becomes important which one you choose. If you're just trying, and there's another one, sorry. Keras is sort of, it's actually it's a higher level interface to TensorFlow. It's easy to use. If you're just trying to crunch data with deep learning and you don't really care how you're not going to tune you're not going to really make a custom deep learning approach. You're more interested in just taking a known approach and applying it to data, then Keras is probably a good place to start. I think the equivalent in PyTorch is PyTorch Lightning. Lightning? Anybody who's PyTorch Lightning, please comment in chat if you agree, if it's very similar to Keras or like a high level interface to PyTorch. Is that right? I'm not a PyTorch expert. I've only been using it for a year or so. I've been using TensorFlow for several years and JAX for a couple of years. Any other questions? Any questions from the audience? Limited audience? No? Cool. One thing, oh, we discuss feature correlations as well. So traditionally, you worry about feature correlations, especially in traditional machine learning. So you always kind of have to worry about if you have, so traditional machine learning is you need to pick the features. So you need to understand the data a little bit. You extract the features. And once you extract the features, you put it through a classifier like a random forest or some other thing. And therefore, because you're using the features, you need to be careful. Features can become correlated, and then you're just not really helping your cause. And if you have too many features, you run into recursive dimensionality because the dimensions of your data or its feature space is too high, and you have diminishing returns. The great thing about deep learning is that it's data-driven. And so in reality, you don't have to worry about feature correlations, because what happens is that the neural network, right. So Wendy's got a good reply for PyTorch Lightning. Thanks, Wendy. And so what the neural networks will actually do is learn the correct features. So in reality, in a deep learning framework, you should be putting in the data and letting it learn the features. And in deep learning, kind of control and make sure that the main problem you need to worry about is overfitting. So you may learn all of these features, but you may learn all the features that really suit the training data and not generalized enough so that when you use the test set, the isn't as good. So you have an overrepresentation of your features, and that overfits to your training data. If you set up the training data and the model correctly, you will not have feature correlations. The network will learn the minimal representation itself. And so you don't have to do any handcrafting of features. And so you don't have to worry about feature correlations. Hopefully that answers the question. So that's one of the great things about it. It automates all of those processes. That's the critical thing about AI. So you might see discussions online about artificial general intelligence and whether we will be, wiped out because we'll become extinct, or AIs will take over, or AIs are going to be smarter than us. But in the end, some detractors will also say that AI isn't really going to help even improve performance of things. What AI really does do is it automates everything. So we have too much data, too much to consider, and what AI can do is automate feature extraction, pre-processing, and it can do so in a very, very fast manner. Okay. So we're in experimentation covered in tomorrow's crash course. Experimentation, by that you mean how to put a solution together? The answer is yes. Try to solve a very simple computer vision problem and then release all of the code open source. In fact, I've already got the code open source. But that's the idea. So I'll spend the first third of it going through basically how to solve the problem. What are the important considerations? Then hopefully do a live coding demonstration exercise of solving that problem using deep learning, and then hopefully run into some problems and then show you how to solve them. I'm a sort of imaging person, so we're going to probably do a little bit of imaging, computer vision-ish, but the same principles would apply to other data. Or I mean, you TF board or try to visualize some parameter settings. Okay, so that's sort of advanced stuff. So TF board is tensor board. So basically, I think we can have a quick look at that. Yep, I'll try to add that into tomorrow's thing. So basically, if you've got your model training and it's spitting out accuracy, how do you know that that's the best you can get, right? And how do you know that you're not overfitting? And how do you know that those are the best settings? And that's where hyperparameter tuning is very important in deep learning and quite annoying, actually. That's probably where you spend quite a lot of time. So TensorBoard is basically a website that extracts all of the log information. So you can have logging information logged by your scripts or your training process. And TensorBoard is sort of like a pre-made website which can use all of the data from the logs and plot them. So they'll plot your optimization process, plot your accuracy over performance as you train your system. You can see the actual computational graph and things. Oh, yes, of course. Also, in the training next week, we're going to look at GPU profiling, also model profiling and model optimization. Yes, that's right. Wei is going to cover that next week in more detail. Thanks, Wei. I forgot about that. So that's an important step. So Wei has published some recent work where he's able to do 3D imaging, but he could fit into a very small card because he profiled all of his models to make sure that he minimized the latency between memory transfers between the GPU and the actual CPU, but also looking at where he lost performance and where he's actually using the GPU and where he wasn't when he should have been, but also looking at TensorBoard and other things that he used to understand that. And so he built a very compact network that solves an important. And so he will do that next week in the same slot as tomorrow's training as well. All right. Great questions. Thanks for the discussion. I will end this session and the Zoom, but I'll keep monitoring the Slack if you have more questions. And of course, we'll see you tomorrow. The last thing, I might create a new thread, but it'd be great to know, as someone who is attending the Summer of AI this year, or this summer, what you are hoping to see, all right? I'm kind of guessing as to what you want to see. I've asked on Slack, and so I've curated a few things. Oh, and on Slack, by the way, I'll put up some playlists for beginner, intermediate, and advanced on some content for you to watch, YouTube videos, so you can have a look at that. I'll put that up on Slack. But it'll be good to hear from you what you want from this Summer of AI, and then I will try to find the person to help. Okay? All right, I think we'll call it there. Thank you very much for attending. Thank you all those who are watching on recordings, those on Zoom right now, and obviously those in attendance. Thank you very much for coming in person as well, and we will catch you tomorrow. Thanks. No worries. Okay. See you, Zoom.